if we're thinking about a regularly designed, no transformations parent function of the cube root function, we should be able to identify, as was suggested elsewhere in the lesson, that the domain of this function is all real numbers. We can take the cube root of positive numbers, we can take the cube root of negative numbers, and we have a domain, therefore, of all of the real numbers. All of the transformations that we know, so reflections over the horizontal axis, reflections over the vertical axis, translating right, left, up, down, scaling away from an axis, none of those will adjust the domain. So any of the transformations that we know and have used to this point will not change the domain of a cube root function. All they will do will shift the space or change the rate of growth for the cube root function. When we need to worry about the domain is when the cube root function is combined into a larger function with some other functions of concern. So all of the other things that we've talked about as it relates to the domain, no denominators equaling 0. We talked about that with rational expressions. The inside slash radicand of the square root function cannot be negative. We talked about that as affecting the domain. So we're just going to mix in with these cube roots the other things that we know that we need to worry about, and then be very careful about the way that we write the domain. So for our first function, we're going to start h of x is equal to the cube root of x over the square root of 80 minus 5x. Now, in a normal situation, I would look at this cube root and say that domain was all of the real numbers. I would look at this square root and say I need that inside radicand to be non-negative, and I would be off to the races. However, the presence of this square root being in the denominator means that we lose 0 as a possibility as well. So when I write my inequality that I have to solve, we normally would write it so that we were allowed to be equal to 0. We are not allowed to be equal to 0 in this case. We must be greater than 0 because we're not allowed to have 0 in that denominator. Subtract 80 from both sides, divide by -5, and we get that x is less than 16. Writing out our domain very carefully, we can use our set notation. X is less than 16. Or we can write out our interval notation knowing that we're less than 16. The cube root had no effect on the denominator. On the domain. It was merely a part of the function. That part of the function contributed all real numbers as possibilities. So we come here with the extra concern of making sure our denominator is both positive and not 0. All right, let's look at another example. This one we'll call g of x. We've got the square root of 2 minus x over the cube root of x. Now, if you're thinking of comparing this to the previous example, it should jump off the screen at you that the roles are reversed. The square root is now part of the numerator, while the cube root is now part of the denominator. In any normal circumstance, we would say that this cube root function is of no concern for the domain. However, because it is in the denominator, we know that we don't want x to be 0, because if x was 0, the value of the cube root would be 0, and then I would have a fraction with 0 in the denominator. So I know that 0, is not involved. Thinking more about the domain, I know that the numerator, the radicand of the numerator, must be greater than or equal to 0. 0 is welcome back into the party because it's now part of the numerator and not the denominator. 0 is welcome back into the domain, but we're still making sure that our radicand is non-negative. We subtract 2 from both sides. We divide by the -1, and then we get that x is less than or equal to 2. Now, we want to be very careful about the way that we write this, because we need to say that we're not allowed to be 0, and we need to say that we're staying less than or equal to 2. Interval notation would take us up to the 0, union that with 0 up to and including the 2. Set notation, x is an element of the real numbers such that x is less than or equal to 2, and x is not equal to 0. We need both of those things to be true simultaneously. So as long as we are careful with combining our two domain calculations, here x not being allowed to be 0, here x needing to be less than or equal to 2, as long as we're careful with the combination of the two of them, we should have no problem writing an expression or the interval notation or the set notation for the domain.